Thank you. Well, I have a junior and a senior up there, okay, and both of them are in college education, and I happen to work in school education primarily, okay. So what I hope to do is introduce you to some of my friends. I call them my friends, and let's see why those friends are very good and where they may not be of help, okay. So I'll start with some school level stuff, okay, but we won't remain there throughout, okay. Friendly things, okay. More specifically, let's look at this, okay. For class 1, 2, this is something that dominates the life of any child, okay. When you see this, how many of you think of 3 and 2? Just a show of hands. Okay. How many of you think 30 and 2? Okay. Maybe because I spilled place value. Now, doesn't that look as a 30 and a 2 too? Right? That looks like a 30 and a 2. Okay. Now, this is where my first friend comes. When I learned these, I learned them like this. Now, this won't completely explain. So, basically, this is made of 2 cards. Okay. So, 32 always has been a 30 and a 2. A 12 has always been a 10 and a 2, okay? And similarly, I'll go into the other one. So, the physical form of the card will be something like this, okay? You can touch it after the talk, okay? Very easy to make. I use all the posters that go up on various boards in Azim Premji University to make those, okay? But this is even better, right? You can see the 30. In particular, you realize that 30 is a 3 tens. See, with 300, that's not a problem. It's 300. But 30 has to be unpacked a bit more. Anyway, so these are called, sometimes called flats, longs, units. These are the longs and the units. And these are the flats, the hundreds are the flats. Notice that 0 there basically indicates that there is no bundle of tens. Okay, that's what it indicates. There are 300s, 2 units, and no tens. All the tens are included here. There is no 10 outside this big. Okay, now once you have this imagination, so even these are a bit abstract maybe, but when you come to this level, it's very concrete. Now you can do a lot with this if you imagine numbers like that, and it can be bigger and bigger. I'll take a few instances, okay? This one. First of all, we don't realize where we use it. Any thoughts where we use, say, distributivity of multiplication over addition? If you have to multiply some number by, say, 23, how do you do that? What do we use there? There you go. That is more known. This is less well known. Okay? Now what do we typically do? 7 and 8 we add first, then there's a carryover. So essentially this is what we are doing, right? That's where the associativity comes in. And actually what we do involves a commutativity as well, because we do the 7 and 8 first. Okay? This to a class 1-2 child may be too abstract. So let's bring in our friends. That's a 27 and that's an 8. You basically are putting everything together. So it doesn't matter where do you start and which do you club together. You are basically taking account of everything. Okay? Also, if you notice, these are in groups of 5 and whatever is left. Okay? Now, if you play with this enough, you immediately know when you add a 7 and an 8, this will give you a full 10, the top row, and then you will have the 2 plus 3, 5, so you get a 15. Okay? Those little things can get automatized, so you just do them like this, and they're very helpful in the early years. Okay? Now that was at the level of 2. Square root of division algorithm. It's big and there is some complicated things that happen and usually nobody explains why so. Okay? Somewhere you have to separate them 2 digits at a time, and then after the first round you have to double whatever you have got. Okay? Any idea why do we need to double that? Incidentally, that answer is also there in the syllabus, but the links are not made. So, I'll take a friendly number. Okay? So that's that. Now let's try to put it up as a square. Okay, so when we are trying to find a square root, essentially we have a square whose area is equal to that square root, and we are trying to find how long the sides are. That will be the square root. Okay? So that comes. So these are the sides. Right? When we write it, we don't write the zeros. That's what we do. Okay? But the moment you write the zeros, it becomes clearer. And the only reason I could think of it this way is because of my friend. Okay? So that's how much we have left, and you can see that matching, right? So now we are going to put the remaining, and you will see very soon where that 20 plus question mark comes in. So what we have done now is exchange 100 into 10 tens, okay? So let's put one layer. Now what we have added is a 21, right? Notice now we have added a 2 20s and a 2 square, right? So the number of layers that goes, that's kind of the question mark, and we're multiplying by that. Okay? So every place, so this is where the 2 comes. You see 2 sets of tens, one here, one here. That's where the 2 comes. And now if you stare at it, is there any algebra formula that comes to your mind? Any algebraic identity? I cannot hear whispers. Yes, and that's also taught. There is no school syllabus which doesn't include it. And that 2AB, that's what the same 2 is here. That's what the same doubling is happening. Okay, so more exchange. We need more units. Okay. Okay, so now we have exhausted it. Okay, so we have got 5 layers, so it's a 5. Okay. Now, the way the animation was done is just for reference. Ideally, you are supposed to play with that, with these kind of stuff. Okay, this is the 100. And this will be the 10. Okay, again, nobody makes this very easy to make. You get those kind of notebooks, paste it on any card, and that's it. Okay. Now, so as part of my work, I try to look into manipulatives and things which will help children understand what is going on. Okay. Now, when you come to multiplying negative numbers, there are certain issues. Okay, let's take a close look. Now, it can be written the other way, 5 times 1, 5 times 2. I am now taking it this way. This is how we write. Then you know which number is getting repeated and which number indicates how many times it is going to get repeated. Okay? So then, that's not a problem. 3 times negative 5 will mean you add negative 5 3 times and that will give you a negative 15. No problem. But how do you add 5 negative 3 times? No, the answer we know, but how do you explain it? Minus 3 5 times? Then you are assuming commutativity. We haven't established it yet. Okay, so be careful. These things are completely glossed over. You cannot, I mean, ideally in math, you shouldn't assume it. Okay? And then that one, suddenly negative times negative becomes positive. Okay? And everybody mugs it up without understanding how. This is where all manipulatives basically break down. They can't take it forward. If you are interested, take a look at the integer chapter in class 7 NCERT textbook. They have used it, they have done it using pattern without assuming anything. Okay? And it's beautiful. Okay? Class 7. They introduce integers and do addition subtraction in 6. In 7, they do multiplication and division. But what about these? Now we are in the domain of rational numbers. How do you make sense of that? 3/5 of a negative quantity. Okay. Or negative 1/3 of something. Okay. And this is the third possibility, right? So this is where concrete manipulatives don't help. Okay. Now what happens is when you are in whole numbers, everything is discrete and you just count. Okay. When you are in fractions, you can't just count, you have to measure. Okay. There's a level of complexity, but everything is still positive. So you can think of in terms of length and area. With integers, you lose the positive advantage, but still things are discrete. When it comes to rational numbers, both are gone. Okay? But then there is some way out. Okay? Now, one meaning of multiplication that children learn is repeated addition, but with that, I don't know how you can explain this, or even 1/3 times 1/4. Okay? I don't know how to explain it with repeated addition. The meaning that cuts across is scaling. Okay? If I say, for example, my age is twice my niece's age. Okay? And you know my niece's age, you can figure out how old I am. Right? So you're just multiplying by a number. So that's kind of scaling. Now you can reverse it also, something like my niece's age is half my age, right? So then still the meaning holds. Okay. So now this can be done visually. Okay. So you get one number line, that's the baseline. Okay. This is what we are going to scale up, down, etc. And this is the number line, the second one, which will basically tell you what is the scale factor. So let's now choose 4 as the scale factor and see what happens. Okay. So you see 1 goes up to 4, 3 goes to 12. So you can kind of see that how it gets stretched. Right? And as you can go further up, you can actually see whether it will stretch more or less. Note that the two intersect at this 1. Why? How is 1 related to multiplication? Exactly. So when you multiply by 1, no change. Right? Now, if you multiply by any number between 1 and 0, what happens? Shrinks. Okay? Now, you're still multiplying with positive number, but you're multiplying negative numbers. Okay? So the same stretch continues. Now you take a negative scale factor. Okay? See what happens. So the same basic thing remains. You're connecting this 1 to this 0 and it was stretching up at that time. Now you stretch down to this point and you get negative 3 times 1. Okay? And you immediately notice how the positive part goes to the negative. Immediately. And the negative comes to the positive, a kind of crossover. Okay. Now, if you have a larger grid, let's say you have graph paper, okay, then you can put in a 0.2 or a 0.7, etc. And then it does work for rational numbers. You can try it that way. Okay. So, yeah, it looked like, oh, it has gone to abstract. Okay, but there was a way to bring it down. Where do children see number line first time? Where? I mean, not in the textbook, which class? You have all seen it there. Before you knew it was called a number line. Yeah. So that's something that they have to deal with. Okay. Now I'll take a big jump. Okay. I don't know if you have heard of this lady. Definitely search for her and check out this YouTube video. Okay. She struggled with this concept when she was a student like you all. And then she had to teach it. So she panicked. I can't put my students to the same thing I had. Okay? So what she did is she crocheted hyperbolic surfaces. And then all of these things that, you know, in an hyperbolic surface, if you have one line, straight line, you have a point outside that line, you can have more than one lines going through that point, all of which are parallel to the original line. That's not true in Euclidean plane. okay? But that happens on the hyperbolic. Now, when she crocheted it, it just became obvious. Any paper, right? That's a 2D, that's a Euclidean plane. How do you get a straight line there? Right? How do you join the 2 points? You have nothing except just for a paper. Exactly, right? If you fold and crease it, what you will get is a straight line, nothing else. Same thing, if you have any of these hyperbolic surfaces, planes, if you fold it, you get a straight line, okay? And that's how these have been put to. And then you clearly see that, which I can't show you, it needs a 3D thing, okay? I have barely learned crocheting, I can't make a hyperbolic plane yet. But you basically realize if you have that thing on you, this is where they come closest, and then as you go away on either side, they diverge. So they can't meet, and that means they have to be parallel. Okay, this comes out beautifully. Okay, so now one of my colleague who is an expert crocheteer, she's making these, and she's also going to make a half sphere. And on a sphere, we know the typical way of finding a straight line is you put 2 pins and you release a rubber band, the least path it takes, okay? That is the straight line, all the great circles. When flights go from one continent to the other, that's the path they take, okay? So it's used for navigation on Earth. So we thought, okay, why don't we try the folding technique there? So now she's going to make a cap, a hemisphere, and then we'll try to fold and see if that matches the great circles. That's work in progress. Now for a long time, mathematicians thought hyperbolic surfaces cannot be modeled. Done. Okay, not so abstract. And they occur in nature. Anytime nature is trying to maximize surface, this is what is going to happen. Lettuce leaves, coral reefs, many places you come across these things. Okay? Okay. Check this out. Okay? I have looked at the linear algebra part only, and trust me, in ISI we were taught well, Indian Statistical Institute. But the way this guy talks about eigenvalue, eigenvector, connecting it to transformation, it literally blew my mind. So there are other people trying to bring the abstraction down, okay? Because unless you have a sense of, feeling how it will behave, you can't go further too much. You can remember all your formulas, but that will not give you an intuitive feeling of how things will behave. And that's very important. Okay? Now here is the part where I need you to get active. Okay? What I'm going to share, okay, let me just go back. What I'm going to share now is roughly 2 months old. So still pretty fresh. Okay? Not much shelf life yet. So these are 4 points given to you, okay? And the question is that, do they form a square? How would you figure it out? Well, these are all xy coordinates, so very familiar Cartesian plane. How will you decide? Please note, I'm not looking for a yes-no answer. I am asking how will you tackle this problem? What will you do now that you have? Find? Okay. Find distances. Okay, I'll put it up, don't worry. What else? We can find all the distances. How will that help? Okay, so should all the distances, how many possible distances will you get? 6. So 6 distances. Should they all be equal? Okay. 4 will be equal. So let's say 4 should be of the form A. What about the remaining 2? Okay, so if 4 are A, the remaining 2 should be how much? B. And how are A and B related? Okay. Any other option? Anything other than distances? Okay. So how will you get to the angles? Dot products. Okay. Any other thing other than dot products? Anything other than dot products? We are talking 2D. So for Pythagoras, you will calculate the distances, right? Angles, okay. So for angles, you said dot products. I am asking, is there any other way? Dot product is one way. Anything else? I think I heard something. Cross product for 2D, I'm not sure I know how to do that. Maybe you can teach me. Yes, thank you. Right? You can get line segments and you can find their slopes. Right? And then the slopes will have to be something. Right? So again, like the 6 distances, you can probably work out a similar thing for slopes. I'll leave that as homework. Anything else? Thank you. This is the 3rd time I have seen this exercise being done to a group of people, twice with your age group, and both times it kind of comes in that order. So you can see that there is no surprise, right? It's eerily predictable. Now, this is how it looks when plotted. Now, once it is plotted, what do you think? You can join them almost in your head, but just looking at it, are you able to tell anything? Consider this. This is the line and this. So if you think of a rise run, how is it? It's a 4:1. Now look at this triangle. Same, so they are congruent by side angle side. So if you have the grid lines, you just look at it and it jumps at you. Do you need to do any calculation as such? Now, so out of these 3, if you have to figure this problem out for Euclidean plane, okay, Cartesian plane. Which is the friendliest method? Now comes the but. Again, I mean, I have been lazy, I haven't worked out the coordinates, so I don't have them. But suppose exact coordinates are given, not ABCDs. Okay? Coordinates are given, 4 points, 3D. What will you do? Yes, that still works. What else? Right, so there is a chance that the 4 points may not be coplanar. Right, so that also has to be checked. But that's a good idea. Is there any way you can, like in case of the 2D, we could plot them. Is there any way we can do that for 3D? It will be coplanar, but the plane may not be perpendicular or parallel to any of the axes. It can be like this, right? So how do you visualize that? Aha, okay. And how will the projections look? I know, but will they have a particular, I mean, that will give you 4 points and that will give you a quadrilateral. But that should it always be a square? No, right? So that is an interesting question. Thank you for that. Okay, what are the possibilities? Okay, and well, that's a very new good idea. Wow. Okay. Now that needs an investigation. Okay, because if you start with a square and you project, you get something on all 3 planes. Now, is the converse also true? So that needs to be figured out. Okay, good. This is why I like interacting with young people. New ideas come. Okay. Anything else? So we can do distances, we can do projection, what else? Like, okay, but in order to do that, you have to add 4 more points. Won't that become more complicated? Okay. The thing is, where it becomes more complicated is, you know, we basically learn, live in 2D. You know, our notebook is 2D, the blackboard is 2D, our whiteboard textbook is 2D, computer screen is 2D. So when we have to visualize points in a 3-dimensional space, you have no choice to make a model. And in a model, how do you suspend points? Those issues are there. But then we have friends now. This is a free software which you can download, and this has a 3D. And there you can plot them and, you know, turn it around, rotate it, do all kinds of funky stuff, and you can visualize there. Okay, this was done in GeoGebra. So definitely play with it, big friend. Okay. So it can be plotted. It can be plotted. And once plotted, obviously, you know, a lot of, you can basically literally see what is happening. What about this angles business? Can we do anything regarding angles when it comes to 3D? We can do cross product and see, we can also use the dot product. Okay, so this also remains. Okay. So between 2D and 3D, there doesn't seem to be too much of difference in terms of what can happen, except for the fact that now we have got a new idea. Okay? And the fact that plotting is a bit more difficult. I mean, for 2D, you can just take a sheet of paper or whatever and do it. Mathematicians are never easily satisfied. Okay? We are done with 2, done with 3, next bigger number. Okay? Let's now complicate the problem, as one of our professors used to say. Now what do you do? So now the coordinates will be as 4 tuples or 5 tuples, right? Yeah. This guy still works. Anything else that still works? This will still work. Okay? The thing is, we are probably more comfortable with distances and lengths than with angles. And that is why distances are more popular, even though that's a more complicated formula involving a square root. Okay? I mean, though for this purpose, we don't need to worry about the square root. So the advantage of distance formula is that it carries over throughout. It is generalizable, something that mathematicians love a lot. But while learning mathematics, if you focus only on the horizon, only on the generalization, and miss out on, what is really happening, then a lot is actually lost. Because unless you have a good understanding of the specific cases, you won't be able to generalize later. You can use something that somebody else has generalized for you, but to come to that capability of what do you generalize and how do you do that, you need to engage with the specifics for some specific cases and see how that can be generalized further. And that part often gets missed. When we teach existing knowledge, we often give the finished product and don't discuss the process, to reach there. And so you don't get the flavor of how things happen. Okay, now, this is the last bit, okay? So we are going to look into points which are equidistant from each other, okay? So if you want 2 points, it will be like a line segment and it will fit within one dimension, right? Let's say number line. And lazily we can take these 2 points, right? Okay. There's a reason we took this 2 instead of a 0 and a 1. You will see immediately. Okay, predict my next step. 3 points, right? Now will 3 points fit into one line? No. So you have to increase the dimension. Okay? Right? 3 points all equidistant from each other, so that's what you get. And you need minimum 2D. Now you see the advantage of a -1 and a 1? Okay? Now if you can easily plot that, right? So it will look something like obvious next step. Okay? Right? Now, what happens here is, you can kind of imagine that if it's the z-axis coming like this, it will be somewhere here, along this YZ plane, right? Since it's a regular tetrahedron, you also know it will be directly above the centroid. And you know the centroid is 1/3, right? So you have to divide that √3/3. So that's what gets you the 1/√3. And as for the final point, well, it's easy. You kind of try to look at this distance, only one variable remaining, and that you know has to equal 2. So that can be solved. Now, one very clear thing. Never trust a mathematician. I say it to children, adults alike. Okay? If it is mathematics, do it yourself and cross-check. Never trust us. Okay? If you trust us, you are hurting yourself. Okay? So same thing here. Whatever I say from here on, okay, take it with buckets of salt. Okay? Till you convince yourself. So far we could kind of sense what is going on, right? Now it is unavoidably abstract. Unless somebody has some supernatural power, this is difficult to visualize. Okay? Because we have to go to 4D. Okay? Now, if you look at the previous ones, there was a pattern. The first 2 points we got, we kind of embedded them in the next dimension. The first 3 points we got, we embedded that into the 3D, right? So for the first 4 points, we can do the exact same thing, right? So if it was 1, 0, 0, we can just make it 1, 0, 0, 0, and like that. Okay? So the last, that W, the last coordinate can be 0 for the 4 points, and then we just have to find the 5th point, right? Which is equidistance from all of this. Okay. So if you do that, that's what you will get. Again, don't believe. You get that. Okay. That's how you get 4 equations and you get the coordinate. You know, typical mathematician, okay, never satisfied, very greedy, okay. So that will be the 5th point, just put a 0 at the end. Now, when you look at it, do you see any pattern? Are the x coordinates same, different? Okay, y coordinates? Now, what about the z coordinates? So somewhere it seems that they're kind of getting frozen, right? So that's one observation, and you won't get it until you proceed a bit more. Till the, 3 dimension, 4 points, this much pattern didn't reveal themselves. So sometimes you have to walk a bit more to see what is happening, okay? Anything else, especially when you stare at these numbers, two times W by Z, okay, no, okay, but something just from here, 3, 6, 10, 1 plus 2, okay. What kind of numbers are they? There's a name for that. She's absolutely right. Okay. Anybody knows what kind of numbers these are? Okay, I'll just draw them and then immediately you will know. Okay, triangular numbers. Okay, so these are also called, this is called T2, T3, T4. What is T1? Exactly. Right? Okay, so now this is where a mathematician differs from a computer. A computer will faithfully go to the 7, then to the 8, then to the 9, right? Mathematician after this point doesn't want to do that, it is boring. So, is there any shortcut? Right? Now to figure that out, you need to catch these patterns. Okay? Now once you catch that pattern, then you need to look at these numbers, because these are a little bit off. And this thing here. Okay? Now that is again something I'm going to leave as homework, okay? Check it out, and if you do these calculations actually, you will see what is happening, okay? So once that was there, so I then try to guess what the next one will be for 7th. So first I guessed, then I did the calculation, okay? So the first part is intuitive, next part is rigor. And it matched, okay? Now once that testing worked, then you can jump for the big one. Okay, so this is all collated together. Okay, maybe I should have shown you this. I forgot I created this. Okay. Anyway, so this is all together. And okay, so this is the first three like that. Then you work backward. Okay, so this is the last point. And, oops, sorry. Up to here, these are all the triangular numbers. Okay, then it's triangular number with something else. Okay, don't trust. And then you can work backward from there. So if you do few steps, then you finally can do the general step. Okay, so the beauty here is at this level you have to abstract out. Okay, and that's where math becomes really powerful. You have already probably seen, or you will, where we need to think beyond 3 dimensions. Okay, there are many spaces where we need to deal with 4 variables or more, etc. So there is this whole thing about, Rn, real number times real number, like that. So this is the thing. Thought of n-dimensional space is something that is used, has lots of application in various places. But then to deal with that, you have to abstract out, and at the same time when you do that, suddenly somewhere things come up. I had no clue that triangular numbers will be lurking behind somewhere. I still don't know why triangular numbers, why not hexagonal numbers or square numbers? Maybe one of you will figure that out. I don't know. Is it because any 3 points will form a triangle? I don't know. But it was fun doing it. And most of the people who are involved with math, who love math, okay, that's for the fun part. It's not necessarily easy, but it's a lot of fun. Okay. So